good afternoon, everyone. How many of you have tried MoonBit before the? Okay, cool. So it's a good time to introduce MoonBit to you guys. So MoonBit, the name comes from the moon and the rabbit. So you see the picture. It's a moon and a lovely rabbit. And it's a WebAssembly, the first language. So it also supports other backends. I will talk about later. So a bit about me. So I already played with a lot of language before I started working on MoonBit. I made a script, which was called BugScript, in the last 6 and 7 years. And I was also a contributor to OCaml and Flow. Of course, I also play with a lot of toy language. Since it took very long to develop a community behind the language, so MoonBit will be my final one, all-in commitment. And the experience on working on a script actually gave me something unique. It's because I implemented the most parts of the whole tool chain for script in the initial version. So I understand the value of the tool chain, the vertical integration, because I write the compiler, the build system, and the standard library. So I do all of the major stuff for the script. Another thing unique about me is I'm very sensitive about the compilation performance. So even the RISC compiler is so fast that someone in the community asked, why the RISC compiler is so fast? Because we give out something? Actually not, because I really care about the compiler performance. This made me connect with my first job when I was working on a medium-sized C++ code base. So when I just made a silly typo, it takes me 20 minutes to see there's a typo in the code base. I need to redo the work. So I deeply appreciate the feedback loop. I want the compiler to be as fast as possible, so I don't need to waste my time in compilation. Yes, so this is today's topic. I will first introduce what's the MoonBit and why, and then the MoonBit and WebAssembly for the browser, and then the third one is the MoonBit and WebAssembly for the server-side programming. And the last one is the MoonBit outside of the WebAssembly use case. So I think you already know all the benefits of WebAssembly. So I just see the key features of WebAssembly is very fast, and it's portable. It's also small, compact encoding, and it has gained some market share, but it doesn't have going wild. So my observation when I studied MoonBit is I found the WebAssembly has a huge potential, but there's something lacking. We have lots of very good WebAssembly runtime, like the Wasm time, Warmer, but we don't have good producer. So when I studied MoonBit, only like Rust and C++ can give you a small code size, but for other language, all major program languages support WebAssembly, but even like a Hello World could generate very big WebAssembly output and took a very sophisticated tooling to set up when I studied MoonBit. I think it's still mostly the case if you took the mainstream language, like Golang. Even for Hello World, it generated 1.8 megabytes when I did the experiment. This defeats the purpose of WebAssembly. The benefit of WebAssembly is a very compact, very tiny to be used as a glue language. But even for Hello World, it generates huge output. Then I cannot use WebAssembly as a plugin because it's too large. I cannot use WebAssembly as a UDF for the database because it's too large. The other one is Rust. It generated a small code size, but it's very good for the system programming. But if you use it in as an application developer, if you use a day-to-day language, it's fine. But if you leave Rust for a while, like you leave Rust for 6 months and then come back, then you need to relearn the Rust. That's my experience. And the last one is the JavaScript. People even compile the QuickJS as an interpreter to the WebAssembly, then use the JavaScript on the WebAssembly side. That's also, in my opinion, defeated the purpose of WebAssembly, right? We want WebAssembly because we want performance. Now we use the JavaScript, use another level of interaction, which defeats the benefits of WebAssembly. So that's why I made the MoonBit. So it's a program language which is designed for WebAssembly, we want the WebAssembly output to be as small as possible, even smaller than Rust. And of course, keep the benefit of WebAssembly to make sure it's run fast. The last one is the compilation performance. We want to make sure the language compile as fast as possible. Also, we are focused on the dev experience and tooling. The last one is WebAssembly first, but not WebAssembly only language. Because if language itself only compile the WebAssembly, then the language may remain a niche language. You want the MoonBit to be used as much as possible. So the right graph is shows some key metrics when we announce the MoonBit. The first metric is the running time. MoonBit is close to Rust, slightly slower than Rust, but it's much faster than Go. And for the output size, MoonBit generates half the size of the Rust, much smaller than Go. And for the compiling time, actually, it's also the fastest one. For the real world, because this is just a tiny benchmark, for the real world large code base, MoonBit is much, much faster than this benchmark. I think it's the 10 to 100 times faster than the Rust compilation. So the key features to summarize of MoonBit. So it's optimized for WebAssembly, generates small code size and running fast. The size is measured in bytes, not kilobytes, not megabytes. It's inspired by Rust, Golang, and OCaml. We have the good parts of the Rust, like the generics, type inference, trace. Another thing I want to emphasize is MoonBit is very, very expressive in pattern matching. So it supports beyond the pattern matching of the algebra data types, even more than that. And we also support the efficient functional programming. Even in loop, in MoonBit, is purely functional, but it gives you bare metal efficiency. So to view MoonBit in another way is most like the Rust with garbage collection or Scala modular unneeded complexity. So what you get back in exchange for much faster compilation and better tooling. So here's a very small preview of MoonBit. We support a very expressive pattern match. So here you can pattern match the data with JSON, like the native JSON pattern match support, and the array and the bytes. And also for the pattern match of the JSON, it's static, means it supports the exhaustive checking. And we are also going to add more customer pattern support, like similar to active view pattern in F#, if you know the F# program language. So another thing quite different in the development of the MoonBit is the IDE and the build system is co-designed with the language on day one. This is quite unlike the history of the most program language. Most program language, for the author just hack the compiler. And then after many years, the language gains some adoption. People will start working on the IDE or build system. But the whole language and IDE and the build system is co-designed together, thanks to my previous experience in the RISC. So it has a very highly parallel and fault-tolerant type checking. Why is this? Because we want to reuse the same compiler code base with the IDE. So unlike Rust, you have like the Rust static analyzer and the Rust C compiler. So when you add a new feature, you have to make sure your compiler and IDE both at least support. So this is not the same case in MoonBit. We share the same code base, and it's very fast, real-time, responsive. And also, we want to care about tooling. So we want to provide the out-of-box debugging support, because in my opinion, the debugging is really important. And we also, besides the desktop IDE, we also provide the cloud IDE, which means zero installation. You can try the MoonBit via URL. And actually, this is quite different from other cloud-based IDE. We don't need the container, just all the IDE compiler running in your browser. And also, the last one also is quite important. We support the native AI completion and the concurrent AI code generation. This is because the project started at the same time as the ChatGPT. So we really care about the AI code generation, but this is not the topic of today. So I will give you a brief demo. Yeah, you can see we have a very easy tutorial. It's an interactive tutorial. You can change the value, and then reach on the program. And then we can even debug the out box. So I can view the debug tools. So can I run the debugger? Yeah, we stop here, and then you can go to the line-by-line debugging. Another one is we have a full-blown IDE run in your browser. Here's another example. I have the Mario Pro game. It's a playable game. I can change the code. I can see the effect immediately effective. So I can change the, for example, I can change the number of the Mario players from 1 to 6. They get instantly. So there's no caching involved, just recompile on the fly. Cool. So let's get to the second part of the MoonBit and WebAssembly for the browser. Since WebAssembly was originally introduced in the browser, so the key use case is when you write your large-scale JavaScript application, you want to move some of your performance important part from the JavaScript to WebAssembly. So which means you need a very good story in FFI between the JavaScript and MoonBit. Thanks to our very tight WebAssembly GC integration, MoonBit supports the WebAssembly GC out of box. And we also take advantage of the latest JavaScript built-in string proposal, which means MoonBit string is just the same as a JavaScript string. So here's a simple example. We take the function called print and concat, take two parameters a and b, which is the string, and return another string. Here, for this simple function, the MoonBit compiler only generates the code, which is 180 bytes, not kilobytes, 180 bytes. And because the MoonBit string is just string, so zero copy. There's no like the byte string. And because we reuse the WebAssembly GC, so it's very easy to debug using the Chrome DevTools. And of course, we want to do some DOM manipulation. It's very easy to do in MoonBit as well. We have a keyword called extern. Extern type will be compiled to the external ref in WebAssembly. Then you define your start function called set CSS. Then you use it in your MoonBit code. Very easy, no scaffolding, and no byte generation. Here, we import the set CSS, and when we need to instantiate the set CSS, very easy, just DOM. DOM is just a Chrome DOM. And then key is just the MoonBit string, same as the JavaScript string. And the value is also the same. So you don't need to macros to generate the boilerplate code. Very easy, very straightforward. And the MoonBit not only give you better performance, but give you more elegant code, in my opinion. Here's one example, the palindrome function generated by ChatGPT. It's actually, so the palindrome means if you read the string from left to right and right to left, it's the same. Actually, it's very hard to implement right because you have to take into account the Unicode. And the JavaScript string is a UTF-16 Unicode, so you have to walk through from left to right and calculate the offset of the code points. And here we use the JavaScript provided Unicode saved API called code point add, but it's not efficient. Here the algorithm generated by ChatGPT is actually an ON2 algorithm because whenever you call code point add, you have to redo the calculation. So how about the MoonBit? Actually very efficient and elegant. Here's the same code in MoonBit. Here we define a function called palindrome and take the input is the string. Then we take the view of the string. The view of string just like the slice in Golang or Rust. Then we pattern match of the view and see if the view is larger than 2 characters. We take the head and tail, see if they're the same. Then we continue the middle view. Otherwise, return false. If the view only have 1 character or empty, then it's also true. So you see the algorithm is obviously correct, but it's also more performant. It's purely functional. It gives you the ON complexity because we don't need to recalculate the index again and again. And it's Unicode safe. Here, even the view itself is allocated on the stack, and we use it's like the functional but in place. There's no heap allocation at all in MoonBit. So this code is elegant, but generated bare metal efficient, like the C language There's no heap allocation at all. So you can check out our website for the real-world example. Here we write a Markdown parser in MoonBit and export to the JavaScript user. The third part is a MoonBit and Wasm for the server side. Because the WebAssembly is an instruction set that doesn't support the I/O. So people frequently ask, how do you read files in MoonBit? How do you write servers in MoonBit? So there are two solutions. One is you write your host API, right? You can just using your favorite host and define the imports. But that's not very portable. Or then we need the component model to the rescue. So we use the WebAssembly interface type to define the standardized FFI. This enable us for the language agnostic and platform agnostic composition. So also give us the better modularity for cloud and edge computing. The bonus point is MoonBit supports two kinds of WebAssembly. One is the WebAssembly 1, which is only WebAssembly linear memory. When you use the WebAssembly linear memory, we have our own garbage collector. It's like a precious GC, precious garbage collector. And if you use the runtime, we support the Wasm GC, then you can use the Wasm GC part. And of course, we still generate a very small code size. So here is the right side is our very simple HTTP server using a component model with a MoonBit. It generates the smallest size among all the language. So it generates only 27 kilobytes, much smaller than Rust, of course, and even much smaller than Python. So also here is a real-world example. We dogfood MoonBit with the component models in our code review AI agent. So the code review AI agent is written in MoonBit using the component model and deployed to the cloud. So it's a very good example. We will talk more about in our workshop tomorrow. So how does it work? We define the interface using the WebAssembly interface types. Then we generate bindings with binding string. And then you write your application logic. Then we use our Wasm tools like we mentioned in the morning, and then compose them together along with the Wasm time or JCO. So because of MoonBit, the component model gives us the language agnostic composition, so we can use the component model to do the reusing existing libraries between different languages. Like we can use the MoonBit essentially with any language which supports the WebAssembly component model. Here's one example. We want to reuse the cheated parser written in C and called from MoonBit. And here is the diagram shows you just write your own string. So the cheated is a very popular parser generator. It's used a lot in the syntax coloring. Here we define the with declarations and then generate the code for both the C and the MoonBit. Then we use the WAC to hook them together. So this is roughly the cheated interface. Here we define two interfaces. One is the language, the other is types. Because the parser is a heap, is a resource. We make it a resource. And then for the same which interface, the C part we export the resource get language, and the MoonBit we call the get language as a consumer. Here's your stub code for the C stub code. So here we export the get language, and then you can consume the library in MoonBit. Here we get language.get language, and then we can use the WAC tool to hook them together. And then this means we can reuse the same code between the C and the MoonBit. Of course, we can do the same thing. You can use the Rust cheated library with the MoonBit as well. Yeah, so as we see, the MoonBit is a very young language. We started the project around 2.5 years ago. So we have a lot of things to improve. And the component model is also a work in progress. We are committed to make the MoonBit the component native language. We will have a better integration between the MoonBit and the Wasm tools. We also to catch up with the latest proposal, like the Phase 5 proposal, and implement the async support as long as it's standardized. And we'll have a workshop tomorrow about how to use the MoonBit and the component. Join us tomorrow. So yes, and the last part, MoonBit, as I said, MoonBit is WasmCloud first language, but it's not a WasmCloud only language, because if it's only a WasmCloud only language, then it will be a niche language. Because we want people to use MoonBit as much as you can. So actually, we support a lot of backends. Like we support the WebAssembly, which I support with linear memory model and the garbage collection. We also support the native. Actually, we really care about native. So actually, we have 2 backends for native. We can compile to C and it can be used in a microcontroller unit. It can be used in a very constrained device. Like for some chips, we only have the 100 kilobytes memory. You can still run the MoonBit in there. And also in the last week, I think we released our new backend can be compiled to the LLVM. So MoonBit can generate very efficient LLVM output. And eventually, in the long run, we want to bootstrap the whole compiler in MoonBit itself. So actually, we aim to bootstrap the front end this year. There are also some very interesting projects in the community, like the people always write the MoonBit LLVM bindings. So actually, we are going to open source the MoonBit compiler toolchain. So we will provide you MoonBit, Yak, and the LLVM infrastructure. The last one is the JavaScript output. MoonBit also can be compiled to the JavaScript output. And actually, it's very efficient compared with the handwritten JavaScript code, because the same backend can enjoy a lot of optimization we did. And the use case, like we port the Elm architecture. We port the Elm architecture called the RabbitT to the MoonBit. And then, so you can also use the MoonBit for the UI code generation. MoonBit is a pretty young language. We started around 2.5 years ago, but we have a very growing community. We aim to reach beta status come out this year. We have experimental async support. Once we finish the async, then we'll be beta. We have our official account on Twitter, and we have a Discord community. We also have at this time, we already have a package manager, and we have a centralized package repo where you can share your libraries on mooncase.io. Actually, there are already hundreds of packages in the website. So that's pretty much everything I want to share with you. You're welcome to join us. We are a very young community, and we welcome new contributors. Thank you.
Yeah, thanks for the presentation. I really like the language and the nice trade-off between simpler language and good efficiency. So technically, I think I'm a big fan of all what you decided and do, but I'm wondering what is is it fully open source? Do you have a business model? At some point, I guess you need to get some funding to develop that. So I would be curious to know more about how do you plan to get some money from the language? What is the sustainability? What is the community and the future to get more involvement from other companies and contributors?
So actually, so most of the MoonBit toolchain, like the build system, standard library, is open source, and the compiler itself is on the relaxed version of the SSPL. But so the relaxed means if you don't make any modification to the compiler, you can just use whatever you want. So as long as you don't make any modification, and the generated artifacts is also free license. You can license your generated code as you want. At this stage, we use it's most like a defensive strategy, because we spend a lot of time to make the toolchain works, and eventually we need some revenue to make it sustainable. But we don't want to provide a VP mode. If you are a regular user, you don't use some features. If you are a VIP user, you use some fancy features. I think it's not a healthy model, because we want to grow the community as much as we can. So we want to give all the cool features to the users. So that's why. But we also want to protect ourselves. So that's why we choose the license. Yeah.
Really enjoyed the talk. Thanks so much. I saw that for the Elm architecture thing that you guys are doing, which I think is a really cool idea, you had to target compilation to JavaScript. I'm curious what was in the way of just being able to do that with WebAssembly the way it was?
You mean the things, I think when you compile JavaScript, this time it has better integration with the DOM API. The Wasm GC give you some accessibility, but it's still not as good as compared with when you just compare to regular JavaScript. Yeah, so, but for the UI, I think the performance is not really that much. Yeah. All right. Cool, thank you.